4.1.3, what ions will each of the following elements form? So we find where they are on the periodic table. We can do this a couple of ways. Some of you already know that anything in the first column, the alkali earth metals, are going to form a 1+ charge. Some of you have that memorized already. In case you don't, let's talk about why that is. So lithium, we need to think about where it is on the periodic table and what its electron configuration is. So we started reading our book up at the top of the book, in the far left corner. We have 1s first energy level. If we don't remember, this is my S group, this is my P group over here, then I've got my D's in the middle, and F's down here. First energy level, second energy level, third energy level, fourth energy level going across, except for these weird D's, they start with the third energy level there. So lithium, 1s, and then I count 2 boxes. That means I have 2 electrons. And then I go down to my second energy level, and it's the S group again, because I'm in that area. And to get to lithium, I just need 1. So this is telling me I have 2 electrons in the first energy level, 1 electron in the second energy level. I have 3 electrons total, 2 plus 1, which is nice because I have 3 electrons total in a lithium atom. But it's going to form an ion. It's going to form an ion in such a manner that it can be in the same isoelectronic series or have the same number of electrons as one of the noble gases. Because the noble gases, we know, electronically and chemically are stable, so it wants to be like those. So the one that it is closest to is helium. If it lost this 1 electron, it would have an electron configuration of 1s2. That one would be gone, so the 2s part wouldn't be there anymore either. So I have 1s2. That's the same electron configuration as helium. So it's in the same isoelectronic series when I have Li as an ion. Losing 1 electron has a charge of 1+. It has 1 more proton than it does electron in its nucleus. That's what gives it that 1+ charge. So lithium would be a 1+, just like that part that you may have just memorized. Okay, but this is the explanation of why that is. The next one, magnesium. Let's clear off, actually let's not clear it off, let's leave it messy. Magnesium is right there. I'm going to read my book the same way I did before. I start with my first energy level. And my first energy level has the S shape. And there are 2 of them. And then I go down in my book, 2s2. And I cross the expanse here, 2p6. But I'm not to magnesium yet, so I go down 1 more level. I have 3s2. Now if I look, I could go all the way over here to argon. I'd have to add 6 more to do that. Or I could go back to neon. That's what makes the most sense to do. So it's going to lose these 2 electrons, so that I have the electron configuration of 1s2, 2s2, 2p6. Now it's in the same isoelectronic series as neon. So it's the same electron configuration as neon, but it's not neon because it still has 12 protons, so it's still magnesium. It's just an ion now. And it would be Mg2+. It has 2 more protons than it does electrons in its nucleus now that it lost those 2. We can see it does have 6 plus 2 plus 2, that's 10 electrons, but we know based off of its atomic number that it has 12 protons. So that's why it's a 2+ charge. And then aluminum, right here, if I were to rewrite the electron configuration, there's just 1 more electron than there is in magnesium, because it's the next one on the periodic table. So we have 1s2, 2s2, 2p6, 3s3. Again, it makes more sense for aluminum to lose those 3 electrons than it is for it to gain 5 more. So it's going to lose those 3, and we're going to become Al3+, and it's in the same isoelectronic series as both magnesium 2+ as well as neon. It would be that 1s2, 2s2, 2p6. Question 4.1.4 says, what ions will each of the following form. So we're doing the same thing that we did with the last one. Let's do it with the shortcut though. So we know everything in this column forms a 1 plus. Everything in this column forms a 2 plus. The transition metals are the oddballs. We can't tell just by looking at them. But then we get back to the boron family. We have a 3 plus. Then we've got a plus or minus 4, depending upon more information, what type of bonding is involved. So it's either a plus or a minus 4. Then we have 3 negative, 2 negative, 1 negative. You can see here it just needs to gain 1 more to be like that one. This one just needs to gain 2 more to be like that one. This one just needs to gain 3 more to be like that one. Since we're adding electrons, it's becoming more negative. So doing this the fast way, we see that phosphorus is in the same column as nitrogen, so it is a 3 negative charge. So it'd be P3 negative. Oops. Oxygen, so right here, it would be a 2 negative. And bromine would be a 1 negative. And we can use those same steps that we did in the last one by looking at the electron configurations and figuring out which one it would be like to be in the same isoelectronic series as a different noble gas. Or we could, again, just memorize the shortcut that everything in that column is a 3 negative charge. Sample question 4.1.6, we are predicting whether the following would be ionic, polar covalent, or covalent. So what we're dealing with here is we're thinking about electronegativity differences. Electronegativity differences. So if I remember, my trend is that as we go from left to right across a period on the periodic table, we are increasing the electronegativity of the elements, and that's just how much it's going to pull an electron from another atom towards itself. So if we look at O2, we're going to see, well, it's the same element, so if I subtract the same number from itself, it's going to be 0. So if I have 0 electronegativity difference, then I have pure covalent, or just covalent works as well. In NH3, I have a nitrogen here, I have hydrogens here, I have an extra electron cloud here. This would be polar covalent. The electronegativities are not different enough for it to be ionic, but they're not exactly the same thing, so it's not pure covalent. NaCl, I have a metal bonding to a nonmetal. They're very different electronegativity values, and since they are very different electronegativity values, when I subtract them, I'm likely going to have an electronegativity difference greater than 1.8, which means it is ionic. So NaCl is an ionic substance. In sample question 4.2.3, we're to draw the Lewis dot diagram for CCl4. So I need to start looking at number of valence electrons. Carbon has 4 valence electrons. So these are my VEs, my valence electrons. Chlorine, I have 4 chlorines, and each of them have 7 valence electrons. So I have 32 electrons total that I'm dealing with. And this I'm going to use as a check later on. I also want to check that I meet the octet rule. And that's where each element involved feels the effects of 8 electrons. So I'm going to put carbon in the middle. And these are covalent bonds. That's what I'm using when I'm using the Lewis dot diagrams. I'm dealing with covalent bonds, so they are sharing electrons. So I put my carbon, the one that needs the most, in the middle. I surround it with the ones that are almost complete, chlorine. Each of these dots represent 1 electron, and each line represents 2 electrons. So if we do our checks, we can check that carbon feels the effect of 8 electrons, and there's 2 there, 2 there, 2 there, 2 there. Sure enough, there's 8 for carbon. The chlorines each feel the 2 plus the 6 non-bonded around it, so that's 8 for each of those. And then I can do my check to make sure I have 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have met the octet rule as well as my total rule. That is my Lewis dot diagram for CCl4. We want to know in 4.2.4 how the bond lengths differ from single bonds to double bonds. My single bond is going to be my longest bond, followed by my double bonds. And then it doesn't ask about it here, but it may ask you on the test. Triple bonds are the shortest. We don't have quadruple bonds, so that's the most we're going to go. So we go from longest to shortest, single, double, triple. 4.2.7, draw the Lewis diagram, name the shape, and write the bond angle for the following molecules. We're going to do CO2 first. It's the same setup that I did before. Carbon has 4 valence electrons. Oxygen each have 6. There are 2 of them. So I have 12, 13, 14, 15, 16 total. So that's going to be part of my check. The one that needs the most to be complete is carbon, so I put it in the middle. And I start out by doing single bonds with the oxygen. If you go through that, though, you're going to find out that you don't have the right total number of valence electrons. So I'm going to do double bonds with each of them. Put in the unbonded electrons. And then I do my check. So 2, 4, 6, 8, carbon's good. 2, 4, 6, 8, each of the oxygens are good. 2, 4, 6, 8, 10, 12, 14, 16, we've met the total and we've met the octet rule. This is carbon dioxide. It has 2 electron clouds, both of which are bonds. This is a linear molecule, which means the bond angle is 180 degrees. Next, I have NH3. My nitrogen has 5. My hydrogen, 3 of them, each have 1. This is an exception to the octet rule. Hydrogen only needs 2. If I start putting more around that, it becomes unstable. So I draw this out. And I have a complete octet, and I've met my rules for total numbers. I have 1, 2, 3, 4 electron clouds, 4 ECs, but only 3 bonds. So this is trigonal pyramid. And that has a bond angle less than 109.5 degrees. H2O is a nice bent shape. We've seen it over and over and over again. We've got 1, 2, 3, 4 electron clouds, but only 2 bonds. This is bent, or V-shaped is another name for that. Water is kind of special. It is a bond angle of 104 degrees. It's generally a little bit larger for that for other molecules that are bent. CCl4 is my last one. Again, I'd go through my steps of double checking, but I'm running short on time, and we've done it already on a different page, so I'm not going to go through it again. But to draw it out at least, there is my CCl4. It has 4 electron clouds, all 4 of which are bonds. This is called tetrahedral, and it is 109.5 degrees. Then it's asking which of those in 4.2.7 were polar, so we go back. The CCl4 tetrahedral shape, as long as all 4 of the electron clouds are the same thing, these will always be non-polar. They end up canceling out their electronegativity differences as long as they are all the same elements that are bonded to the carbon. Whenever I have a bent shape, this is always going to be polar because I have those extra electron clouds there. Makes it polar. Then I have an extra electron cloud here with the trigonal pyramid. That is also always going to be polar. And then finally, the CO2 linear. I do have electronegativity differences, but they're going in exactly opposite directions at the same length, and so they're going to cancel each other out. Linear is always going to be nonpolar as long as both of the electron clouds, or the things that they are bonded to, are the same.